All right, welcome everybody. This is going to be a recording of the remaining part for the assumptions lecture, week 4 in class lecture. We will begin with influential observations. We made it through the assumptions and diagnostics stuff in the live lecture, so now we'll record the influential observations part. So, what is an influential observation? Well, it's pretty much what it says on the tin. It is an observation that has too much influence on the results of your model estimation. And that influence can come just by kind of pulling the regression line too far toward itself. So this is a case that may just, overly influence the slopes or the intercepts or whatever. Or it can cause problems by invalidating assumptions, by violating the assumptions. So extreme values, for example, may not follow the normal distribution when the rest of the data follow the distribution just fine. So you're violating the normality assumption, not because the data as a whole aren't normally distributed, or the residuals as a whole aren't normally distributed, but just because you have one or two really extreme cases that live way too far out in the tails of the distribution where they wouldn't under the normality assumption. So those are the types of situations we're dealing with here. Those are the types of cases that we're trying to find. And we can break these into kind of two distinct flavors of a problem: outliers and high leverage observations. So an outlier is a case that has an extreme Y value, an extreme outcome value. So their value of the dependent variable is very unusual relative to the rest of the data. So this isn't an absolute extremity, but relative to the majority of the data, the Y variables here are too large or too small. They're just too far out in the tails. Okay, so these are basically values that fit the model very badly. They don't sort of live where they should, given the standard distribution that we assume for the residuals. Okay, but outliers are about extremity in the Y dimension. The second case we have are high leverage observations, and these are extreme in the X dimension. So high leverage observations are observations that have extreme predictor values relative to the rest of the data. So it's the same idea as an outlier. You have some X variables, X values that are really, really large or really, really small. They're really extreme relative to the majority of the X data. But the difference here is that we're talking about variables that live on the right-hand side of our equation, not the dependent variable. So it's worth differentiating these two types of influential cases. Are we talking about an outlier, which is an extreme Y value, or are we talking about a high leverage observation, which has extreme X values? Okay. Sometimes you hear these called like outliers on Y versus outliers on X, but we're going to talk about outliers as being strictly the extreme Y values. So identifying outliers is pretty straightforward, because we just want to find values that are really large after we've accounted for the model. So we do that by looking for large residuals. So residuals quantify the distribution of Y after we've accounted for our model. And if there's any really extreme residuals, those cases are potential outliers. So the problem is we don't want to directly look at the residuals themselves, because they may not have a constant variance, right? So, we may have some kind of heteroscedasticity thing going on, and we want to, we don't want that messing up our check for extreme cases. We don't want to be flagging cases as extreme because we have heteroscedasticity. Also, we would like to have things on kind of a unitless metric. So we're going to standardize the residuals before we try to detect outliers. And by standardize, we basically just mean we're going to create z-scores. So we're going to subtract the mean and then divide by the standard deviation. But we're going to do this in a little bit of a special way. So what we want are so-called externally studentized residuals. That's the specific flavor of standardization we want to apply here. If we just apply the usual z-scoring, that would be internally studentized residuals. That's what we would be producing there, internally studentized residuals. And that's, those residuals are a little bit of a problem because if there are outliers in the distribution, those outliers will pull the regression line toward themselves. That's why they're influential, because they exert too much influence on the regression line. Now, the residuals are defined by subtracting the regression line, the predicted value for a given point, from the actual data value for that point. So if the data value is an outlier and it's pulling the regression line toward itself, clearly it's going to have too small of a residual, right? It's pulling the line toward itself, and the difference between that line and itself is what defines the residual. So internally studentized residuals aren't they can kind of hide outliers. So what we want is a special flavor of residual, so-called deletion residual. And this is a concept that's going to come up in several of our tests, or several of our indices here. And the idea is this. So we take our nth observation, we're calculating the nth deletion residual here, and we subtract from it the y hat value for that observation, but this y hat value was calculated in a special way. So this y hat value comes from a model that was estimated using all of the data except for the nth row. So basically, we calculate the y hat value using all the data except for the observation we're trying to check at this moment. And we do that for every observation. So we get this deletion residual, which is a residual that won't be contaminated if yn is an outlier, right? Because it's not going to be used to estimate this best fit line, so it cannot pull the best fit line toward itself, right? So this is going to be the foundation of our externally studentized residual, which we will call T sub n, where we put the n in parentheses like this to mean that we have calculated it excluding the nth case. And then the standardized residual is kind of what you would expect, right? We take that deletion residual that we calculated on the previous slide, and we divide it by the standard error of the deletion residuals, the same way that you would calculate any t-statistic or any z-score style standardization. So these T sub n here, these externally studentized residuals, have two nice properties. One, they're all scaled equivalently. So we can look at for extreme values and not have to worry about potential heterogeneity, kind of telling us that some cases are outliers when maybe they're not. And they are students T distributed. So these are distributed in the same way as the t-tests that we've been doing to check our regression slopes and that kind of stuff. So we could technically do a significance test for these, but it's, you end up with like some really, really crazy repeated testing issues going on there because you're doing one of these for every row of data. So you have like hundreds of repeated tests. So it's really better just to kind of look to see if there's any that are particularly extreme. So a common cutoff is 3, for example, because that would mean that this particular residual is 3 standard deviations away from the regression line, basically. Like this observation falls 3 standard deviations above or below the regression line, which is quite a big deviation, right? Where the standard deviations are in terms of the standard deviations of the residuals. Okay, so we can use this as just like a blind cutoff to do screening, just throw out anybody who has a studentized residual greater than 3, absolute value greater than 3. But really, the better way to go about this is, again, graphically. It's best not to just automate this process blindly, because, it may happen that you have kind of quite diffuse data, and you may end up throwing out more data than you want to if you just blindly automate the process. So what I prefer to do with these is to create index plots. And an index plot is basically what you get if you plot some value, some continuous value on the y-axis, and you don't really specify an x-axis in R. So here we're going to plot just the student as residuals. So we can get the student as residuals by using the rStudent function applied to a fitted model object. And if we just give it just y data with no x, it's basically going to plot the y values against the row number, so against the index. So each one of these is one of our student as residuals for a given observation, where the observation number is given on the x-axis. And this is perfectly fine because we don't really care about the observation number. We don't need to look for any trends here. What we're trying to find are cases that clearly stand out from the crowd, to use a colloquialism. So things that appear to be qualitatively different. So this point here is a clear culprit. So this guy looks definitely suspicious. And indeed, the student as residual for this guy is above 6. So he's more than 6 standard deviations away from the regression line. That's very extreme. But the nice thing about the visuals is we don't have to get so bogged down in exact cutoffs of +3 or -3, but we can say, oh, this guy is clearly in kind of a regime of his own. That's a very likely candidate for an influential case. Maybe also this one down here, but it's not quite as extreme. This would be the one we should consider first. Okay, so I really like index plots for this kind of an inspection, because you can just look at them and apply the interocular trauma test. Does it slap you right between the eyes, right? If it does, then that's a potential situation you need to deal with. So this guy, for example, passes the interocular trauma test. He stands out like a blow between the peepers, and you know that you need to do something about this case, most likely. All right, so the outliers are pretty straightforward. We can just look at the residuals. We have to scale them, but we can just look at the residuals. The high leverage points are a little bit more tricky. If we only had a single x variable, then we could basically do the same thing. We could calculate we could just look for the univariate outliers in that one variable using some kind of studentized, some kind of standardization or a box plot method or whatever method you want to use to find univariate outliers. But usually when we're doing regression, we have more than one predictor, right? We have a multiple linear regression model. And it's not necessarily clear how you should evaluate influence on all of those points, all of those x variables, because a high leverage case, a case that has influential x data, doesn't necessarily have to have any single x variable being really, really extreme. It can just be a very unlikely combination of x data, right? So for example, if you're looking at climatological data, and you have the number of hours of sunshine during the day, and you have the amount of rainfall in the day, and the number of hours of sunshine during the day is 14. It's been basically middle of the summer, sunny from sunrise to sunset, no cloud cover at all. But also you have 10 hours of rain in that day. Those two are unlikely to occur, right? You don't usually have sunshine and rain at the same time. So even though maybe it's perfectly possible to have a day that's sunny from sunrise to sunset. There's nothing particularly unusual about that. I mean, there is in the Netherlands, of course, but not if you live in, more pleasant climates. And of course, it's perfectly possible to have a day where it's raining all day. That's not unusual either, unless, of course, you live in the desert or something. So those two values by themselves aren't necessarily extreme, but when we put them together, they become very unlikely. So that's a suspicious observation, and that would probably be a high leverage point. It's unusual with respect to the rest of the climate data in our sample, so it's going to have too much influence. So we need some kind of a measure that can simultaneously account for all of the influence of all of the x variables at once, and we use the leverage values to do that. So the leverages are actually calculated during the model estimation. There's a specific way that we can estimate the regression model that uses these leverages. It's well beyond the scope of this course to talk about exactly how that works. But basically, we calculate this hat matrix, and it's called the hat matrix because it puts the hat on y. We can use it to basically calculate the y hat values. And it's a function of the predictors and various things. And the diagonal of the hat matrix, the h sub n, so we're going to have one, the hat matrix is going to be n by n, and the diagonal entries are going to be our leverages. So we get one leverage for each row of data, and that leverage tells us how extreme the predictors are relative to the rest of the X data that was used to fit the model. So if we have any X values with high leverages, if we have any observations with high leverages, that's telling us that the combination of X values for that particular case is very far from the sort of average X, the mean vector for X, relative, that we use to fit the data. So in simple linear regression, where we have only one predictor, this is the formula for the leverage. Again, we have one for each row, so this is the formula for the nth leverage. And in the numerator, we just have kind of like a sort of the variance contribution for that one case, right? We have xn minus the mean of x and squared. So to calculate the variance of x, we would do this for every row and then divide by n. But here we're just doing it for one row. So this is kind of the variance contribution of the single case that we're interested in checking. And hopefully it makes sense that that's kind of the thing we'd want to focus on, because if this X data is really, really extreme, then this variance contribution for the X case is going to be really large, right? The difference between X and the mean is going to be really big. So that's kind of the core of our measure. And then in the denominator, we just have the cross product of the of all the X data. So this is just the variation, the unstandardized variance, where we take every row, every X, subtract it from the mean, and then we square it. So this is just the variation, the unnormalized variance. So we're getting here kind of a proportion, like how much of the total variability, which is this term in the denominator, is attributable to this one specific case. And if it's too much, then we say that case is too influential, right? So again, I don't think it's super useful to pick a hard threshold. People have recommended various thresholds you can use for automatic screening, but I definitely prefer to look at these things graphically, just like with all of our assumptions. And in this case, an index plot is, again, an excellent way to do this. So leverages are always going to be positive. So we only have to look for values that are high on the graph. We don't have to look for any negative values. And creating these plots is also very simple. So we just use the plot function, generate a base R plot. And the hat values function is what we can use to generate leverages. So hat values will generate the leverages. Again, the reason it's hat values is because we're taking the diagonal of the hat matrix. So that's where this name comes from. And here we're again looking for things that are kind of qualitatively distinct from the other cases. So to my eyes, these three observations up here definitely stand out. as being potentially problematic. Maybe these two, but to a lesser extent, they could kind of be viewed as sort of connected to this data down here. It depends on how strict you want to be in your screening, but these three up here definitely seem to be in a regime of their own. So those would be the ones I would consider first if I was trying to think about observations to be deleting or to be treating in some way. Okay. Oh, incidentally, I should potentially mention, like, why are we using base R graphics all of a sudden? Like, up to this point, we've been kind of asking you to work with ggplot, and now we're suddenly using a lot of base R graphics. You can certainly create these same plots using ggplot, but honestly, it's not usually worth the effort. You can see that it's very, very easy to make this quick and dirty index plot here. And it wouldn't be that much harder to do it in ggplot, but it would take several lines of code, and you'd have to remember, you know, like all the kind of semantics of ggplot. And it's not worth it in this case because when we're doing diagnostics, regression diagnostics, and outlier screening, we're not generally trying to create publication quality figures. We're usually using these figures as tools that we're going to then use to make decisions in our analysis. But we're not probably going to put these in our paper. We'll provide the code, you know, that we use to do this analysis. You should always provide the code you use to do your analysis as a supplement to your paper so people can regenerate the plots if they want to. But we don't need to worry about these things being super beautiful, right? They're just a tool to give us an answer. So that's why we're reverting back to the kind of ugly base R plots that we had left behind when we learned about ggplot. All right. Now, we at this point have two different flavors of influence. We have these outliers, the extreme Y values, and we have the leverages, the extreme X values. But we don't necessarily care whether a case is an outlier or has high leverage. What we care about is whether or not it's influential. So does it affect our model too much? A case may be sort of technically an outlier or technically have high leverage, but maybe it doesn't really affect the model that much. Like, it doesn't change the estimates, it doesn't change our inferences, it doesn't change our predictions, in which case we should probably just let it be, right? There's no reason to throw out data if it's not having a deleterious effect on our model. So what we care about is the influence that these cases are having. And we could certainly, you know, check the individual outliers, check the individual leverages, try deleting them, see what happens. But there's a class of screening tools called measures of influence that simultaneously consider both outliers and leverages in one metric, and then give us kind of an answer about which cases are most likely to influence the model, whether it's because they're high outliers or because they have high leverage or both. And it's usually the cases that are extreme in both that are the most problematic. If a case is both an outlier and has high leverage, that's going to pretty likely be an influential case. If it's only one or the other, then high leverage cases are usually worse than outliers. And the reason for that is simply because we treat the X variables as fixed, right? So the Y variable gets a distribution, and we have an error term that accounts for misfit in the Y dimension, right? We're modeling the mean, we have some variability. So outliers, they have to be kind of more extreme because they really have to be totally messing up the distribution of Y. But high leverage points, they really have much less wiggle room because we don't assume a distribution for the X variables. The X variables are assumed to be measured without error, and they're assumed to be correct. So if we have an extreme X value, it's just thrown into the mix with no error correction. It's just, hey, you know, you might be a totally extreme case, but as far as the model knows, this is perfectly valid data that's not going to be attenuated in any way. So high leverage cases tend to be the more problematic of the two. But we would now want to look at these influence measures that combine the two ideas into one nice little check. And there are two flavors of influence measures. There are measures of global influence and coefficient-specific measures of influence. The measures of global influence are things like Cook's distance, DF fits, and the idea here is we want to see how much does this one case, we're always looking at one observation at a time, how much does this one observation affect the overall fit of the model? Like how much is it moving the whole regression line, the whole best fit line? Yeah. The coefficient-specific measures of influence are looking at the effect that this observation has on one regression coefficient at a time. So DF betas is the most common coefficient-specific measure of influence. DF stands for difference, beta obviously for the slopes, the betas, and S is for standardized. So this is like standardized difference in the betas. Not the most elegant name. So we have a DF betas for the intercept and then for every one of our slopes. So there's two different flavors of the thing we have here. And the way that these things work is basically using the same logic as our deletion residual. We're going to essentially compare a model estimated using the whole sample to a model that has been estimated using a sample wherein the nth observation is excluded. And if there's a big difference between those two fits, then we say the nth observation is very influential. So for those who are interested, these are the explicit formulas for the Cook's distance and the DF betas. And the idea of the Cook's distance is in the numerator, we kind of calculate the sum of squared, well, it's not really the sum of squared. It's kind of like a sum of squared deviations, but what we're subtracting here is the y hat values from the whole model with all of the observations from the deletion y hat values. This is kind of the difference. This quantifies the difference between those two models, the one where n is excluded and the one where n is included. We square those deviations and we sum them, and then we divide by this, basically the standard deviation. We kind of standardize the difference. So this is kind of like a sum of squared, a mean squared error sort of thing. But we're comparing kind of the deletion model to the non-deletion model. It turns out that the Cook's distance also has a formulation explicitly in terms of the standardized residual and the leverage values. So this is the internally standardized residual, the internally studentized residual. But we can write it in terms of the internally studentized residual times this ratio of the leverage to 1 minus the leverage. And then there's this weighting term out front. The specifics here aren't really important. It's the logic that you want to get, that we're comparing these two flavors of model. And based on that comparison, we'll be able to tell whether the nth observation is having a substantial effect. Likewise, the DF betas follows a similar logic. We compare basically the coefficient estimate from the full model with all of the data to the coefficient estimated from the data with the nth observation excluded. So again, we have this kind of the same sort of deviance that we had up here, except now it is only for one coefficient at a time. So beta here is going to be the intercept and then every one of our slopes. And then we just divide by the standard error from the reduced model, the one that leaves out the nth case. And just like all of the measures that we've seen so far, I think the best way to evaluate these is in terms of an index plot. So it's very easy to calculate the Cook's distance in R. We use the Cook's.distance function, and we just apply it to our fitted model. And then if we just plot that the same way we have been before, we're going to get an index plot. And again, we're just looking for those points that stick out. So in this case, this observation and this observation look to be the problematic ones. Okay. And in case you've been worrying like, okay, well, now I see that these are the potentially bad observations. What the hell do I do about it? We're going to get to that in a few slides, so don't worry. So for the DF betas, when we calculate df betas, which we can do with just the df betas function, we're going to get a matrix as the result, where we're going to have one column for every coefficient, including the intercept, and then we're going to have a row for each one of our observations. So in this particular model, we only have, it's a simple linear regression model, so we only have an intercept and a slope. And here we plot the df betas for the intercept and the slope. This extra part here is just to give it a title. So this isn't actually necessary to plot, but we're giving it a title so we can tell which of these plots has which. And again, we just look for those cases that stick out. So this observation looks like it's pretty influential for the intercept. This one as well. Down here, this observation looks pretty influential for the slope. This one as well. I'm not sure if those are exactly the same observations. They might be, they might not be. And in case you're wondering, why would you use a global versus a local estimate of fit or estimate of influence? It really comes down to a bit what part of the model you care most about. So the global measures of fit are not of fit, the global measure of influence, like Cook's distance, are generally a pretty good thing to check, because if an observation is messing up the overall fit of your model, then that's bad. Like, you want your model to be sort of a valid estimation. You don't want it to be overly affected by any one case. So you should probably always check the Cook's distance or something similar like the df fits, which we're not going to talk about here, but is similar. Now, whether or not you want to check the df betas, it kind of depends on if you have a specific parameter estimate that's really crucial. So if you have like one slope or a number of slopes that are really important for testing your hypothesis, then you should probably check the df betas and make sure that they're not influenced first. So you would start by, for example, checking the Cook's distance, and then maybe you find an influential case and you exclude it. Then you refit the model, and then after that you can check the df betas and see if there's any cases that still affect your core parameters after you've dealt with the one that affects the overall model estimation. Yeah. All right, so let's look a bit at the consequences of removing these cases. So if we find influential cases, things with high Cook's distance, things with high leverage, high outliers, however we want to sort of define an influential case, the usual way of dealing with that is to remove the observation. We're basically saying that this observation is not valid in the sense that it has too much effect on our results. So we don't want to include it in the sample. Like, it's too influential, and that means that it doesn't come from the population that we're trying to generalize to. We want to have a kind of democratic, egalitarian model estimation. We don't want one particular case to be dominating our model fit. So we're going to throw that case out. That's the usual way we go about this. So you want to do this kind of one observation at a time, generally. You want to find the most influential case and get rid of it. And then refit the model and see how things look. And then you can re-estimate. You can check again for influential cases, because after you've excluded a case, it may happen that the cases that are flagged as influential change because your best fit line is going to move a little bit, for example. Also, if you have a couple that are clearly influential, maybe you can exclude, two that are very clearly problematic, or if they have kind of the same distance or something. But you want to do this in very small pieces. Just exclude one or two cases, check and see how things changed, and then try again. So in this case, let's exclude the most influential case according to Cook's distance. And it's actually pretty easy to find this. So if we have the vector of Cook's distances, which we calculated before, we call it CD, we can use the which max function, and that will give us the index for the maximum entry in this vector. In this case, that is the maximum Cook's distance. So that's what we want. That's number 28. So observation 28 has the largest Cook's distance. So according to Cook's distance, that's the most influential observation. So let's go ahead and exclude it and see what happens. So what we have here are two different visualizations. The blue line is the original best fit line, fit to all of the data. And then after we delete this red point, which was number 28, the most influential case, we get the dashed red line. That is our that's our best fit line after deletion. And we'll see that it changes a little bit. So the slope changes a little bit, the intercept changes a tiny bit, but not a huge amount. But just the changes in the regression line itself aren't the whole story. So let's look into this a little bit more carefully. So to exclude this case, we could do it this way. There's different ways you can do it. You can use the subset filter maybe command from dplyr or whatever. Or in this case, we're just going to use the simple base R subsetting. So we're going to exclude the 28th row out of cars 93. So we'll get this new subsetted data set. We'll refit our model using that subsetted sample. And now let's look at the two coefficients. So out 1 is the original fit to the full sample. Out 2 is the new one. And we see that the intercept goes down a little bit. It's more negative. And the slope doesn't change very much at all. It's a little bit bigger, a little bit more significant, but not much of a change. And this change in the intercept is, it kind of looks sort of distinct, but we have to keep in mind that the scaling of this outcome is quite large. So these differences are not huge. Okay. So we're not getting a huge effect on the coefficient estimates, but excluding these cases can also affect variability, residual variability. And this is especially true if the cases were influential because they were outliers, right? Because if they're outliers, then they're necessarily going to increase residual variability. So in this case, we're excluding a case it had a negative residual. It was below the regression line. So if we look at the distribution of the residuals, we see that the minimum value is now a good bit higher than it was before. The maximum hasn't changed very much because we didn't delete any data above the regression line, but the minimum is now come up a good bit. And as a consequence of messing with the residual distribution, we have also changed our kind of model fit information. So our residual variance has gone down. So this was the residual variance before, or residual standard deviation rather. This is the new residual standard deviation. And because of that, our R squared has gone up. So this was the R squared before, and now this is the R squared after deleting the case. And with a bigger R squared, naturally we have a bigger F statistic. So we've improved the fit of the model, even though we haven't really affected the actual slope, the best fit line, that much. So to see an even more dramatic illustration of this, let's look to see what happens if we remove the two most extreme cases. So this is still number 28, but now also number 59. And to do this, basically, we are going to do a little pipeline here. We're going to sort the Cook's distances so that they're in ascending order. And then we are going to take the names of those, which is just going to give us basically the row numbers of the original observations. We're going to take the tail, the last two of those. So here we have sorted, we've taken the names gives us the row names. We're taking the two biggest. So these are now the row names for the two biggest, and we're converting that back to numeric. It turns out it's 59 and 28. 28 is the biggest, 59 is the second biggest. So these are the the observations for the largest coexistence and the second largest coexistence. Now, if we exclude both of these, you see that the regression line basically doesn't change, because excluding this influential case below the regression line and another one above the regression line has kind of balanced out. And we have basically no change in the best fit line itself. And if we look at the estimates for the original model and the one with both of those cases excluded, we see that borne out. These are very, very similar, nearly identical lines, best fit lines here. But if we go look at the distribution of residuals, now we see quite a substantial effect. So not only has our minimum value come up, but our maximum value has come down a lot. It's less than half the size of what it was before. And because of that, our residual variability has decreased quite substantially. So this is a big drop in residual variance relative to what it was before, which means our R squared has just skyrocketed, basically. It's like 8% higher, almost 8% higher than it was here. That's a huge jump just by deleting two cases. There are thousands of papers published that have a model R squared that is in total not even 8%. And we've gained 8% explained variability simply by deleting two influential cases. So naturally, the F statistic also takes a huge jump. So we're fitting the data much, much better here. Not because we've changed our model in any way, but because we've removed noise from the data. So we've removed garbage, and we're better able to explain what's left over. So even if removing your influential cases doesn't have a substantial effect on the best fit line itself, it may still be worth doing because you might get much better model fit as a result. Okay, so our last topic here is going to be a general summary of how to treat influential points. As we discussed, the most common method is definitely just to exclude them, just to delete the cases and refit the model. This approach usually works just fine. It's very simple, but it's not necessarily foolproof. We have to recognize that when we're excluding an influential case, we are kind of doing a like a sample screening step. So we're excluding that case from the population that we're trying to generalize to. We're basically saying the population that we want to generalize our results to doesn't include people that look like this extreme case, right? So if you take kind of a classical trope of income, people who are outliers on income, like your Jeff Bezos and your Bill Gates and whatever, they're going to be outliers if you put income in as a dependent variable in any of your models, and pretty much any sample, unless it's, relative to the top 1% of the 1% of the 1% or whatever of the world's income, they're going to be pretty extreme outliers. So if you fit that model, those cases are going to be flagged as influential, and you probably want to exclude them if you want to get any kind of a reasonable estimate for the relationships of quote unquote normal people with regular incomes. But when you do that, you're basically saying that I'm just trying to tell a story about normal people with regular incomes. I don't want my results to apply to the Jeff Bezoses of the world. Yeah. And anytime you do an outlier exclusion or exclude an influential case, you're making the same type of statement, even if it may not be as extreme, sort of clear cut in an example. You're still doing kind of a subsetting of the generalizability of your results. So you have to keep that in mind before you just go crazy with throwing out tons and tons of cases. It's still usually worth excluding really influential cases, but it's not something you should just do without any thought at all. Which brings up the question, what could we do if we didn't want to exclude the cases? And you do have some options here. I mean, certainly you can just fit your model to the data, including the extreme cases, and you're going to get basically results that are valid, but they're going to be really, really strongly influenced by the by those extreme cases. And to the extent that the extreme cases violate some assumptions, maybe your results are not necessarily valid. Depends on exactly how they're influencing the results. So one thing you can do is not exclude the cases, but use robust regression procedures. And this is kind of a broad topic. There's lots of regression procedures that can be considered robust, but there are several different kind of flavors of robust regression that unfortunately we don't have time to talk about in this course. But the idea is usually either that they kind of downweight extreme cases, or they trim extreme cases during the estimation in some way, or they model something other than the mean of the distribution. So like quantile regression models, say the median of the distribution, which is not susceptible to influence by outliers. So there's lots of different flavors of robust regression that you can use to deal with these situations if you really want to keep all your data. You don't want to throw anybody out, but you have cases that are really messing up your results. Perhaps you can look into trying some robust regression procedures to deal with that. And that will do it for our recording. We're now done with our assumptions in diagnostics and influential cases lecture. So I will wrap this recording up here, get this posted, and I will see you all online this time, not in person, online this coming Monday. Thank you very much for your attention.